right, page 245, we want to finish up section 4.3, looking at how the derivative affects the shape of the graph. And the last thing that we need to look at from this section is the second derivative test. Now, the second derivative test tells me the same thing that the first derivative test does. It tells me about maximums and minimums. So it's not a different test to find something different. It's a different test to find the same thing. First and second derivative tests find the same thing. So here's what the second derivative test says. Suppose that the second derivative is continuous near C, and C, of course, we're referring back to the critical numbers that we have already found. It says if the derivative at C is equal to 0 and the second derivative is greater than 0, then your function is going to have a local minimum at C. If the derivative at C is equal to 0 and the second derivative at C is less than 0, then your function has a local maximum at C. If, however, and this is not written there, but they go on to discuss this a little further on, if, however, you have a critical number where your first derivative is equal to 0, but your second derivative, when you plug that critical number into the second derivative, you get a 0 value, then that just means that the second derivative test is inconclusive. I can't tell anything from that. I'm going to have to go back to first derivative test or something else because it's just inconclusive. So, for example, if we have y is equal to x to the fourth minus 4x to the third, in review of what we had done yesterday, we would have gone through with the first derivative test. We would go through first and find our critical numbers, right? So we're going to take our derivative and set it equal to 0. There's nowhere where that derivative doesn't exist. Nowhere I get like 0 in the denominator or negative under an even indexed radical. So no other critical numbers, just where the derivative equals 0. So I would take out the greatest common factor, and then I'd set each of my factors equal to 0. So 4x squared would give me a double root of 0. Double root is significant on my sign graph, so I need to remember that. And then I'd get a single root at 3. So when I come down here and I make a sign graph for the first derivative, I've got a double root at 0, and I've got a single root at positive 3. So then we would pick a test point. Maybe I pick a positive 1. And since I'm trying to find a sign graph for the derivative, I plug that positive 1 into the derivative. So if I take positive 1 and I plug it into this derivative, I'd get 4 minus 12, so definitely a negative value. Cross a double root at that critical number, the sign changes twice. So it appears to not change at all. It's going to stay the same. And then cross a single critical number, I just got x equals 3 one time, the sign does change. So I can look at that and see, we had said from the first derivative test, anywhere that your derivative changes from negative to positive, that means that your original function had changed from decreasing to increasing there, so you'll have a relative minimum there. We had also said that if your sign does not change at a critical number, that means that you don't have anything there. There's not a maximum or a minimum there. And that was a really helpful thing from the first derivative test, that it cleared up some ambiguity that we had previously. So if I had done this completely by first derivative test, I would find out that I have a relative minimum at 3, and that's the only relative extremum that I'm going to have. All right? So if I did this exact same thing by the second derivative test, then I'm going to go back and take the derivative of my first derivative. So the derivative of 4x cubed is 12x squared, and the derivative of negative 12x squared is negative 24x. So there's my second derivative. I'm not setting it equal to 0 or solving it or anything like that. I'm just plugging those critical numbers where the derivative had equaled 0 into that second derivative. So I'm going to test 0 and 3. So if I plug 0 into the second derivative, I get 0. And remember that that means it's inconclusive. I don't know what's going on at 0. I might have a maximum there, I might have a minimum there, I might have nothing in there, I don't know. But if I plug the positive 3 into the second derivative, I get a positive answer. So we found out that whenever we got a positive answer, that meant we were going to have a minimum value at that point. And so that would lead me to say I have a minimum at 3. They typically want the whole ordered pair. So if I know my x value, I got to plug back in to find y. What am I plugging back into? Original, first, or second? Original, right. It is the minimum on the original function, so I plug that 3 back into the original function to find the y value. If you're asked to give a maximum or a minimum, you can get away with just giving the y value, or you can get away with giving the whole ordered pair. You cannot just give the x value. The x value is where the maximum or minimum occurs. It is not the maximum or minimum. So I would have to find that negative 27 there. Okay, so pros and cons. When you're working with the second derivative, sometimes it's more complicated than the first derivative, right? Unless I'm working with a polynomial, and then in that case, it's almost always easier to work with. So I kind of have to look at the scenario that I'm in. Is the second derivative easier to work with or harder to work with? And that might be an indicator to me as to whether I want to use it. Another drawback of that second derivative test is that if I get an answer of 0, I have to go back to the first derivative test anyway, right? Plus, in order to get these values to plug in, I have to go ahead and find the first derivative and set it equal to 0 to get those values. So my thought is, if I've already done all of this work right here, how much longer is it going to take me to make this sign chart? I mean, less than a minute, right? So if that's all I have to do then to determine where I would have maximums and minimums, I'm most likely going to continue with that process as opposed to launching into finding a whole nother derivative and plugging values into it that might not lead me to an answer when I'm done with that. Now, there are times when the second derivative test is helpful. There are times when we're looking at FRQs where the explanation that they give is based on the second derivative, or they ask us a question specifically about the second derivative. If they gave me a graph of the second derivative only, I don't want to have to go back and try and create a graph or even a sign graph of the first derivative from that if I can look at the information on the second derivative to answer my question. So it has its place. I think we'll find that we use the first derivative test a whole lot more than we use the second derivative test because they do the same thing. So over on the top of 246, it says, note, the second derivative test is inconclusive when the second derivative at c is equal to 0. In other words, at such a point, there might be a maximum, there might be a minimum, or there might be neither. Additionally, and this is important, this test also fails when the second derivative at c does not exist. Okay, here's why that is so important. If I'm looking for maximums and minimums, if your function came to a point, okay, so you had an increasing piece and you had a decreasing piece and they met at a point instead of at a curve, you're going to have a relative maximum there, but because you have a corner or a kink in your graph, it's not going to be differentiable at that value, right? So you're not going to be able to find that maximum because you're not going to be able to take the derivative at that point. So when they say right here that where the second derivative doesn't exist, I'm going to have a problem, right? Because I'm going to have lots of places where I would have a corner in my graph and have a maximum or a minimum, but I wouldn't be able to take the derivative there, so the second derivative wouldn't exist there. And I'm not going to be able to find that either with the second derivative test. So it's okay to have that tool to utilize as long as we are very familiar with its limitations so it doesn't keep us from coming up with some correct answers by using it. So again, if the second derivative at a critical number equals 0, it's inconclusive, or anywhere the second derivative does not exist, the test is also going to fail. So it says in such cases, you're going to need to just go back and use the first derivative test. In fact, even when both tests are applied, the first derivative test is often the easier one to use. Okay? So again, it is nice to have as a resource, but I think we'll find we'll be using the first derivative test predominantly. Okay, we had mentioned that this topic of related extrema and concavity and interpreting information about graphs from functions and vice versa was extremely important. On the AP exam, quite often there is an FRQ that deals with this type of information. If not the entire FRQ, at least a couple of parts of it do. And so I have a whole packet for you here that we're going to look at together today of specific information about this type of problem. I'm not sure what's wrong with the poor little full country analysis. Maybe the same thing that's wrong with the poor little state. Okay, so this is not the first sheet in your packet. You'll just need to flip through a little bit perhaps to find this sheet, but this is the one that we want to start with. All right, so to begin with, I just tried to go through and give you like all of the information in a summative form that we have already talked about, okay? So your critical number is going to be wherever your derivative is equal to 0 or wherever your function is not differentiable. If you have a relative maximum or minimum, it is going to occur at a critical number, but not all critical numbers are going to be relative maximums and minimums. You have to test them. Okay, so that's our warning here. How do I test them? Well, you have two choices. You can use the first derivative test or the second derivative test, or if you have your graphing calculator for that portion of the test or quiz you're looking at, you could look at the graph to see whether you had an increasing piece switching to a decreasing piece, or something along those lines. If they ask you to justify it, however, you are still going to have to use the first derivative test and the algebraic explanation. So the first derivative test says if your derivative changes from positive to negative at a particular point, then you're going to have a relative maximum. Now, that would also mean that your original function changed from increasing to decreasing. So we want to note that and make sure we're making that connection. However, that is not what the first derivative test says. And when it comes to AP, they want you to state the first derivative test. So they will not accept it. If you say the function changed from increasing to decreasing at this point, they won't give you credit for that. You have to say the derivative changed from positive to negative at this point in order for them to give you credit for relative maximum. They want to see you know the first derivative test. All right. If your derivative changed from negative to positive at a value, then you're going to have a relative minimum there. And again, that would imply that where your original function changed from decreasing to increasing. The second derivative test says that if you take those values where the first derivative was equal to 0 and you plug them into the second derivative, if you get a positive value, you have a relative minimum. If you get a negative value, you have a relative maximum. If you get 0, it's inconclusive and you have to go back to the first derivative test. All right, then when we were trying to determine concavity, which is concave upward or concave downward, we said your function will be concave upward anywhere your second derivative is positive, and concave downward anywhere your second derivative is negative. Now there are also implications for that with the first derivative, right? Remember we talked about anywhere your original function is positive, anywhere your original function is increasing, your derivative is positive, right? So where this first derivative is increasing is where the derivative of it, the second derivative, will be positive, right? And anywhere the first derivative is decreasing, then the derivative of it, the second derivative, will be negative. So although this is primarily the definition that we associate with concave upward and downward, information about the second derivative, you also can determine concavity by looking at your first derivative. So if you were on a portion of a test or a problem where it said, looking at this graph of the first derivative, tell me where your function is concave upward and downward, I don't have to sit there and make a graph of the second derivative. That would not be fun. We know how to do it, but it's very time consuming. I don't want to do it more often than I have to. So I don't have to make a graph of the second derivative in order to be able to figure out my concavity. I can just look at that first derivative and say, wherever the first derivative was increasing, I'm going to be concave upward. Anywhere my first derivative was decreasing, I'm going to be concave downward. And so we want to really pay attention to that here because that's not stressed It's not often even in the definition of concavity. The definition of concavity usually revolves around the second derivative, but we can also use the first derivative here to be a big help to us. All right, then we said that a point of inflection was where your curve changed from concave upward to concave downward, or vice versa. So that would be where your second derivative changed signs. So we need to be really careful, because although I can find possible points of inflection by setting the second derivative equal to 0 and looking at where the second derivative doesn't exist, very much like we do up here for critical numbers, I still have a warning, very much like what we had for critical numbers, that just says all points of inflection are going to occur where the second derivative is equal to 0 or where it's not differentiable, or where the second derivative doesn't exist. But not all of those are necessarily points of inflection. You have to test it. You have to make sure that there's a sign change. So the sign has to change from positive to negative or negative to positive. So your function's changing from concave upward to concave downward or vice versa in order for you to have a point of inflection there. So again, where the second derivative would change signs. All right? Then, a lot of times, a picture is worth 1,000 words. So I also went through and took all of that we just had verbally and put it kind of in a pictorial form that would be an easy reference guide for us. Okay? So let's look at the comparison of the original function and the first derivative. Anywhere your original function is increasing, your first derivative is positive. Anywhere your original function is decreasing, your first derivative is negative. So where that function changed from increasing to decreasing, or where the derivative changed from positive to negative, we would have a relative maximum. And we would have identified that possible value by setting the derivative equal to 0 and seeing where it wasn't differentiable to get my critical numbers. And if I take one of the places where the first derivative is equal to 0 and plug it into that second derivative and get a negative value, that would also tell me that I have a relative maximum there. Anywhere my original function changed from decreasing to increasing, I'd have a relative minimum there. That's also where my first derivative changes from negative to positive, and I would have identified that possible value by finding the critical numbers, and I could have also tested with the second derivative, and I would get a positive value for that one for my relative minimum. All right? If we do a similar comparison with the first derivative and the second derivative as we're thinking about concavity, anywhere our second derivative is positive, we're concave upward, and where our second derivative is negative, we're concave downward. Where our derivative is positive is where the original function was increasing, and where our derivative is negative is where the original function was decreasing. So we also then can say that where the first derivative changes from increasing to decreasing, I also would have a point of inflection there, or where it changed from decreasing to increasing. I can identify those possible points of inflection by setting my second derivative equal to 0 and seeing where it's not defined. Right? So that gives us kind of a summary for our relative extrema and our concavity. All right? Then there are others of you that you really just need, give me the facts and give me an example of it, like right there with it so I can see it. So for instance, if we talk about, okay, your function is concave upward where the original function is increasing and where the second derivative is positive, and it's concave downward where the first derivative is decreasing where the second derivative is negative, then look at an example of that. Here's my original function, and if I find its first derivative, I can go through and also find my second derivative. So here's my original function, and looking at that original function, I can see concave downward to here, concave upward here. The first derivative, you'll notice, is also decreasing to that same value of positive 3 and increasing from that same value of positive 3. And you'll also notice that the second derivative is equal to 0 at 3, and if we looked at the sign graph, the second derivative is negative on that interval from negative infinity to 3, and it's positive on that interval from 3 to infinity. So I could have seen it on my first derivative graph. I could have seen it on my second derivative sign chart. I can see it on here, but I can't tell exactly where that change occurs, where that point of inflection is. And so, of course, the point of inflection is where that derivative changes signs. Just that same warning again about we have to check our points of inflection just like we do our critical numbers. Just because I get a derivative equal to 0 or a second derivative equal to 0 does not ensure that I'm going to have a critical number or a point of inflection there. I have to test it. And so then we also came down and just gave an additional example of the second derivative test for relative maximums and minimums. All right, this last sheet that we want to look at is extremely important because this is from AP. They don't often put out a guide about a topic, and in this particular case, they are telling me exactly what they want me to write on the AP exam in order to get the points for the work that I do. So this is pivotal for us, and we'll review this again in the month prior to the AP exam when we're studying for the exam. But here's what it says. Sign charts by themselves should not be accepted as a sufficient response when a problem asks for a justification for the existence of either a local or an absolute extrema of a function at a particular point in its domain. All right, here's what they're saying. Let's say that you were working on a problem, you're looking for maximums and minimums, and so you go through and you take the first derivative and you set it equal to 0, and you find out that you have a critical number at -1. And you graph that on a sign graph, and you pick a test point and plug it in, and you find out it's negative over here and it's positive over here. So if you wrote that on your paper and you said, therefore, I have a relative minimum at x equals -1, you would not get credit for that. That's what they're saying, that in itself, if that's all you give them, that will not be accepted as sufficient response for justification. Okay, then what do they want? They want to know that you know the first derivative test. The first derivative test says you have a minimum where your derivative changes from negative to positive. I know that's what you wrote right there. They just want you to put it in a sentence to show them that you know what that first derivative test says. So it says, a sign chart may contain all of the necessary information to make the conclusion that you have a local maximum or minimum, but the development committee and the chief reader want to see that you know what it is about that information that enables you to make the appropriate conclusion. We want to see the student demonstrate a knowledge of the first derivative test by recognizing that there is a relative minimum at x equals 1 because the derivative changes from negative to positive there. The word because is not required, but it is a useful indication that the student has the reasoning. So here's what they want. They want you to say there's a relative minimum at 1 because the derivative changed from negative to positive. Yes, I know you wrote that up there. They want you to write it in a sentence form, okay? So it says, note that it also would not be sufficient justification to say that because the original function changed from decreasing to increasing. I know that means when the original function is decreasing, the first derivative is negative, and when the original function is increasing, the first derivative is positive. But that's not what the first derivative test says, right? The first derivative test says you will have a relative minimum where the derivative changes from negative to positive. That's what they want you to write. So down here it says, here's what would be acceptable. It would be acceptable to give as justification that your function is decreasing to the left of 1 because the derivative is negative, and it's increasing to the right because the derivative is positive. So they want you to state the derivative is negative over here, it's positive over here, so because it changed from negative to positive, according to the first derivative test, that's why I have a minimum there. All right, here's something else that's important. On a closed interval, the justification of an absolute maximum, or minimum can be accomplished by identifying all critical values as well as the endpoints, evaluating the function at each of these values, and then identifying which value of x corresponds to the absolute maximum or minimum. Okay, so if we have an open interval, we are not guaranteed that we're going to have an absolute maximum or minimum. But remember in section 4.1, we had that closed interval method that said if instead of having a function like that, if instead you have something that looks like this where you do have endpoints on this, you are guaranteed now that you will have an absolute maximum and an absolute minimum. So the way that we found that was we went through and we found all the relative maximums and minimums, because they can be absolutes, and we also checked the endpoints, right? Now, In looking at this function right here, I can look at that and see that my absolute maximum is going to be up here. It is not going to occur at that endpoint. However, if I want to get all of my points for this problem, it says on a closed interval, the justification of an absolute maximum or minimum can be accomplished by identifying all the critical values and the endpoints and evaluating the function at each of these. If you look at that graph and you say, okay, I know that's my maximum, so I'm not going to bother to check that endpoint right there, they'll take off points. Because then they don't know whether you knew or not to check your endpoints. So you still have to show that you checked each of your endpoints and you checked each of your relative extrema, each of your critical numbers, to show them that you knew, hey, the absolute maximum or minimum could have occurred at either one. Same story down here. I look at this guy and I say, okay, I know that's not my absolute minimum. I know this is going to be my absolute minimum, so I'm not even going to bother to test that one. They'll take off points. So you've got to show them that you checked every single one of those, okay? So right up here, remember it says evaluate the function at each of those values. On an open interval, which was like the guy we had up here, on an open interval, the only points that need to be considered are the critical values, but students must indicate that they have considered what's happening over the entire interval. So, you know, if I say, okay, I know that I have a relative maximum right here, why do I know that? So they go down here and kind of give you a little more explanation. The justification for an absolute minimum, I'm sorry, not relative, not what we're worried about here, only absolute. The justification for an absolute minimum at a value would require the observation that the derivative was negative for all the values less than it and positive for all the values greater than it. All is so important there because it's showing, look, I've considered this whole function. I've looked at all of it, and this is the only one point where this is occurring. It said it would also be correct justification to find a value to the left that's negative and a value to the right that's positive, and then observe that that's the only critical point for the whole function. So again, you're saying, look, I've considered everything. So they just need to see that you have considered all possibilities, okay? So here is our homework for tonight on pages 247 to 248.